All right, going back to this, ignore the numbers here because I just made them up. But this is our titration curve here. And we want to pinpoint the equivalence point and the half equivalence point, that kind of stuff. And so when we analyze this, we can come over here, we can put in grid lines. Here we're putting in vertical grid lines to help us find the equivalence point. But where exactly is the equivalence point in this plot? Where is the equivalence point? The equivalence point would be in the center of this rise here, somewhere in here. Now, how can we pinpoint that point? Well, one thing is we could eyeball it. Another thing is we could draw in lines to help us figure out where it is. And so let's see. How do I insert graphics? Basically, well, what you can do is you can just do it by hand. And so what we would do is we blow up this region and then we draw a line. You see that would extend this flat part out here, another line that extends the flat part out here, and then just one line that follows the rise in the pH here. And then we just dissect it in half, so that we can pinpoint where the equivalence point is. And so the equivalence point is around here. There's no data right there. And so what we do is we just go down and figure out how many milliliters it took to get to the equivalence point. Does that make sense? And so that's one way to analyze this. And you're going to be analyzing this. And so we can draw in vertical grid lines and horizontal grid lines to help us analyze that curve. But there are other ways we can analyze that curve. And one thing that you notice is that the slope, the slope starts off small and then rises almost vertically here. And then it goes down again. And so if we make a plot of the slope at different volumes of base, we generate this plot here, shown in pink. You see it? This is a plot of the slope versus milliliters base. And you can see it peaks right in the middle here. And at that peak there, that should be the first equivalence point. So this pink plot is called a first derivative plot. It comes from calculus, and the problem with our first derivative plot is we might not have data. The peak might be offset. Let's take a look. Do you see when I blow up that peak, that peak really should be symmetric because, the slope smoothly rises and then smoothly decays. But when you look at this peak looks asymmetric. Do you see that? The reason it looks asymmetric is because of the way Excel fits the data. This fit here of our data is called a smooth curve fit. I'll show you what that looks like here. Okay. Excel, when you have this dialog box with the format data series, you could do a smooth curve fit or this fit. Take a look at the difference. When I don't do a smooth curve fit, it draws straight lines between all the data points, between actually the two adjacent data points. When I do a smooth line fit, then Excel uses an algorithm to kind of calculate, what the smooth transition would be. But we already know the shape of this curve. If it's a symmetric curve like this, do you know what the shape should be? A bell-shaped curve. This should be a bell-shaped curve, or what's called a Gaussian curve. Gaussian is what people normally call it. And so Excel is not fitting our data to a Gaussian. That's one of the things about Excel. Excel is not made for analyzing scientific data. Excel was originally made for analyzing business data, right? And so in business, they don't do Gaussian fits frequently. In science, we do Gaussian fits all the time because we normally expect our peaks to be Gaussians. And so if this were a scientific graphing program, then you could do a Gaussian fit with just one push of a button, or it automatically does it for you. Unfortunately, we don't do it. And so this is usually what I assign as extra credit. Extra credit would be, you can do a Gaussian fit in Excel. It's just a bit more work, and you have to find out how to do it. It's not so easy. And so if you want to do a Gaussian fit, do a Gaussian fit. But do you think the smooth line fit is good in Excel? No. Now, the smooth line fit isn't good because that doesn't look symmetric at all. And so what would be better is if you can't do a Gaussian fit, mathematical Gaussian fit of your data, then the next best thing is to hand draw it. Because the smooth line fit is not going to tell you, where do you think the center of the peak is? To the left like that? No. And so there's a problem with Excel here. And so you could leave the smooth line fit there and then draw a nice Gaussian by hand to fit it. And the very top of the peak in the Gaussian fit should be your first equivalence point. Does that make sense? Or your equivalence point? Okay. So this is called a first derivative plot. In the first derivative plot, we look for the peak. Now this peak here should match where we analyze the equivalence point to be in the pH titration plot, like so. And so the number you get from the blue should match the number you get from the red within experimental error. It could be a little bit different, but you don't expect it to be dramatically different. And so this is just additional confirmation. A lot of people find it easier to get the equivalence point from the first derivative, but that's assuming you got a nice symmetric peak here. Now, there's one more plot we can make from calculus, and this is overlaid here, and that is called a second derivative plot. All a second derivative plot does is it takes the slope of the first derivative plot. And so if we look at the first derivative plot, the pink here, the slope pretty much starts out at 0 and then goes big and then goes 0 again. So the slope starts off kind of 0 and then goes big and then goes smaller to back to 0 and then falls down the other side. When it falls down the other side, it goes negative. And so the slope goes positive, 0, negative. Where it goes 0, where it passes through the y-axis, should be our equivalence point here. And so do you see how the slope goes big falls, goes through 0, and then goes negative. I need to draw in the x-axis there so you can see. Where the line intersects the x-axis, that should be the equivalence point. We also have a problem here because we're trying to define these structures based on a few data points. You know, there's not that much data in that. You know, if we had tons of data, then it would be a different story. But when we have data, my data is heavily biased because my data is all made up. You know, I made the first derivative asymmetric, but this one I made pretty symmetric. Do you see it? But that doesn't mean your data is going to look very symmetric, you know, because you have real data there. And so I see it here. You know, it passes. I can pinpoint where it passes through the 0, and hopefully all 3 match up. One of the problems is with the second derivative, since you don't have that much data, and since the slope, you know, with random error, what happens with random error? With random error, you know, the points fluctuate up and down. And so all of a sudden you could have positive slope, negative slope, positive slope, negative slope when you're going point by point, you know. And the slope is fluctuating all over the place. And we call that noise. And so sometimes these plots can be very noisy because they're just fluctuating considerably. So we're going to make these 3 plots, and we can analyze them by hand as well. The 2 things are going to be extra credit, easy extra credit. Well, not necessarily easy, but one is fitting the first derivative with a Gaussian. The other is generating what's called a Grand's plot. This is the whole Grand's plot here. The Grand's plot plots the H plus versus milliliters of base. When the H plus concentration hits 0, you know, and it's just extrapolated out because it's really never going to hit 0, right? When it's extrapolated out to hit 0 here, that should be the equivalence point. But you should know how to analyze this by researching the Grand's plot and seeing what it means. And so those are a couple of plots that you could do in addition. All right, so let's take a look at how to generate the first derivative and the second derivative on our regular standard plot. Let me try. Oh, no wonder. All right, so the first thing you want to do is you want to put in your volume. Versus pH. Sometimes if your volume increments are regular, then Excel will recognize this pattern. So yours might not be regular. So one of the nice things about spreadsheets is it'll just continue the pattern. So if we go 1, 2, then You can have Excel fill in the rest. But I'm not sure if you took it at regular intervals. You probably didn't. And so you're going to just manually enter in the data here according to this spreadsheet. So go ahead and do that, and then we'll continue the analysis.